Hello there and welcome to the iRevised Supplementary Series for GCSE Physics. In today's video we will be looking at kinetic molecular theory. Ideal gas laws appear in Edexcel and WJEC, for example. We'll talk about those. Talk about some blackbody radiation type questions. It's a bit of an extension of your basic conduction, convection, radiation type questions. Okay, we won't get into the heating of the home, that sort of thing, which is, I know, big in WJEC. We'll do some calculations when we can, and the last bit of the video is going to be on digital electronics, stuff that you see in OCR. Okay, right, so we are trying to go in through to deeper topics, things which are not covered on the junior certificate but are on various exam boards of the IGCSE or GCSE physics. Okay, so that's why we're not going to get into too much of the other basic things, but we might see the odd question here or there about it. All right, let's begin. All right, let's start things off here with the WJEC paper 3 from June 2015. There's an experiment here where we've got a small amount of air trapped here in a tube, and this top part's open to the atmosphere. There's some mercury here, I suppose, and we're going to raise the temperature with some water, and we want to see what's going to happen to the volume of that amount of air when it's heated. We know from Charles's law there should be some sort of increase in volume, and we can see here that as temperature increases we have an increase in that length. Okay, of course the cross-sectional area of that tube will be constant. Okay, that's the results. They've asked us to plot the graph. I've gone and done that already. They didn't give us the horizontal axis, so I've put that in, and I've drawn, even with kind of a ruler on the tablet, a best fitting line here. It's 3 marks, so you probably get 1 mark for the best fitting line, maybe 1 mark for the axis, 1 mark for the points. I'm not sure. We'll have to take a look at the mark scheme. How does the value of the kinetic energy of the gas particles change as the temperature decreases? Well, as the temperature decreases, the kinetic energy should also decrease. The average kinetic energy decreases. State the value of kinetic energy. Well, we would imagine at absolute zero to have 0 joules of kinetic energy is what we would expect to see. Okay, and yeah, so what's this, a 4 marker? We've got a butane gas cylinder. In the winter, its temperature is at -3. The pressure is this. In hot summer, the temperature increases to 42, whilst the volume remains constant. So this is a P1 over T1 is equal to P2 over T2, the gas law or the Gay-Lussac law. So what do we need to do here? Right, so the maximum pressure the container can withstand is this many newtons per square meter. So let's see if that's possible. So P2 is equal to P1. Those are on opposite sides of the equal sign. I'm going to bring T2 up here, and I'm going to have a ratio of temperature times that initial pressure. Temperatures need to be changed into Kelvin, so we're looking at 315 over 270, and that'll be times this 3 million pascals. I get 3.5 times 10 to the 6 pascals, or Newton per square meter. And we can go as far as 4, so I would say there is no danger, everything's safe. Comment just no danger, it seems to be below the value, so that seems to be fine. Let's take a look at the mark scheme. Scale added to the temperature axis. Good, I did that. Points, all points there, and a best fit line. It decreases 0. Good. There's the ratio we did. 1 mark for converting the temperatures. 1 mark for substituting in all the values in the right spot. 1 mark for manipulation and answer, 1 mark for your comment. It's fine, no danger. Okay, and here we have a June 2017 paper 3 from the WJEC, and they've got a table of values here, and they've asked us to plot volume of balloon versus the balloon depth. Okay, now we know the deeper the balloon is, the greater the pressure will be on it. So instead of being inversely proportional to pressure, we're going to see that we're inversely proportional to balloon depth. And that's what the question is. Describe the relationship. I would say it is inversely proportional. I know the mark scheme might say something else. Double I, at what depth would the volume of the balloon be? 5 meters cubed. I would say I count over 4 squares. And that's 10 to 20, so 4 squares is going to have to be 14 meters. Give a value for pressure of the atmosphere. and state how you obtained your answer. Are they talking about for this depth? It seems to me it's going down 100 kilopascals for every 10 meters. Yeah, well, I guess if it's going down 100 every time, and if I'm 10 meters below, yeah, so if I go back up to 0, I suppose that's going to be 100 kilopascals.
Check out the big brain on Brad.
That's kind of a tricky question. That is atmospheric pressure, is 100 kilopascals.
You got a gift, my friend. You got a gift. Oh, yeah. You figured that out. That's why you are who you are.
Okay, and explain how can you tell the temperature of the gas of the balloon remains constant? You're not going to see anything from the graph. What about from this chart here? Well, this is the amount of energy is constant. Because it's in kilojoules, yeah? Pressure times volume is the same thing as work. And so if the amount of energy is constant, we're not losing any heat energy, okay? And no heat energy has been added or removed from the systems. That might be my guess. Okay, and so here for the marks, you get 2 marks for all points plotted correctly, and then you get a best fitting curve, which is 1 mark, and no thick, wispy, double, or wobbly curves. I want to point out that when I drew this, I find it easy to start down here and kind of move your hand away from, okay? And I did it in one smooth curve. Don't leave double lines. Don't do any sketching like this sort of thing, okay? You're not in art class. Connect those points. As the depth increases, the volume of the balloon decreases at a decreasing rate. Oh, wow. WJEC, do not accept inversely proportional.
Oh, come on!
Did that go the way you thought it was going to go? Nope.
Wow, that is interesting. Because that is something I would tell my students. And that is a correct answer. They are not going to accept it. They want you to say that as the depth increases, you see the volume is decreasing, but it's not linear, it's decreasing at a decreasing rate. They're being real sticklers about that. Wow.
No, sir, I didn't like it.
Wow, unbelievable. So know your exam board. That might be acceptable in AQA or Edexcel. WJEC, not liking it in this case. They might like it for a circuits or like a Ohm's Law question, but not in this case. Okay, double I, yeah, we had said 14. The pressure is 100 kPa. Because each time the depth increases by 10. So you're working backwards up in the chart. That's a bit of a tricky question. And then this final one, the product of P and V is constant from the table, and the energy is constant. And if the energy is constant, it only happens if the temperature is constant. Yeah, because if we were to increase the temperature, we would increase the average kinetic energy of the particles. And since that's been told to us as constant, it means that we know the temperature is constant. Okay. Complete statement of Boyle's law is 1 mark. Yeah. I don't think stating Boyle's law is proof of anything. They want to know in this situation, and you needed to look at that table to see that the energy was constant. All right, another IGCSE from 2013. This is a January paper 1. Use ideas about particles to explain how the gas causes pressure on the inside of the container. Okay, we'll do a very basic definition of what's going on, but you know that pressure is the force divided by that surface area. You've got particles moving around colliding. When particles collide with that wall, they exert a force, and the sum of all those forces from all those collisions exerted over that inner surface area is what the pressure is. I guess we could add a little kinetic molecular theory. We could say that particles of the gas are free to move around. They move randomly and quickly in a straight line unless they hit a wall, and then that pressure they exert is going to be the pressure. Let's see what they say. Particles are in constant motion, always moving, yes, random directions, colliding with the walls, exerting a force on the wall, and causing a pressure. So this is what I had said. Okay, but you could also just talk about the particles' behavior moving in a straight path unless they hit a wall. Okay? What do we got here? How would increasing the temperature of a compressed air can affect the pressure inside the can? Well, it would increase. We know that pressure is proportional to temperature. Explain your answer. As average kinetic energy will increase, the particles are moving faster. When the particles move faster, they exert a larger force on the wall of the container. It's a greater force per same area, so increased pressure. Write that out. Okay. All right, part C, we've got a can. It's got a volume of 400 cubic centimeters. The pressure compressed is inside is 5 times the atmosphere. So I'll write 5 atmospheres. The final pressure is going to be released to 1 atmosphere. And they're asking you what is the volume that would occupy to be at 1 atmosphere. Okay, so you've got your Boyle's law, P1 V1 equals P2 V2. We're solving for V2. That's going to be V1 times a ratio. P2 is going to go down to the bottom. There's my little ratio. It doesn't matter what the units are. We'll just keep it in atmospheres. It's going to cancel out. We're going to have, you know, that's basically going to be 5 times the 400. So that's going to be 2,000 cubic centimeters. Does that make sense to you? We are at a very high pressure. When we lower the pressure by a factor of 5, we're going to have to increase the volume by a factor of 5. So in order to get that volume down to 1 atmospheric pressure, it's going to need to take up 5 times the volume. I hope that makes sense. And the pressure would increase. Average speed, average kinetic energy. So they've said collide with the walls more often. I said at higher speed. Higher speed means a larger force, but it will be more often because there will be less delay between particles bouncing around, I suppose, from one wall to the other. So, yeah, they will hit harder. I said they will have, because they're traveling faster, there'll be a larger change in momentum, a larger force exerted. But yeah, walls more often, I guess. That's fine too. Here's the equation. We got 2,000. Awesome. All right, another WJEC. This is from June 2016. It's a paper 3. You're on holiday in Denver. You pack a sealed water bottle with only air. Denver, of course, is known as the Mile High City. It's much higher altitude, so the pressure will be lower. Okay. When he arrives, the water bottle is crushed because the outside pressure is greater. Cardiff is at sea level. Okay. Here's a graph. Here's some other information. Use the graph to write down the air pressure of Cardiff. Okay, well, sea level. So the air pressure at Cardiff is 100 pascals. That's what they call an atmosphere. I thought it's supposed to be 101.3, but well, that's fine. Okay, what else do they want to know? All right, what else do they want to know? Calculate the atmospheric pressure in Denver and use information. Yeah, okay. Is this a Boyle's law? I feel it might be. Calculate the pressure in Denver. What was the pressure before? Okay, we've got 100 kilopascals now, right? So Denver was originally 5 times 10 to the negative 4. Cardiff is 3 times 3.8 times 10 to the negative 4. Right, I hope this makes sense. We've got a volume ratio there, and so we know that the ratio is going to be, and again, we don't even need to worry about this. That's the same. I'm not going to bother putting that in my calculator. Okay, and it looks to me like the atmospheric pressure was 76 pascals. Okay, so lower pressure, of course, because of this ratio. This ratio is less than 1. We would expect that because you've got a higher pressure on the bottom, which means we will get a lower initial pressure in Denver. All right, so we need a 76. 10 squares to move 20, so that's 62, 64, 66, 68, 70, 72, 74, 76. So 76, and that runs along to here, and I'm going to say it's about halfway through that second square. So I'm going to put that about there. This is 10 squares for 500. I'm going to guess is that 1575. Does that be 1600, 1800? Oh. Yeah, because this would be 1600, 1700, 1800, 1900. Yeah, okay. So I'm going to go 1575. Calculate the temperature required for the bottle of Cardiff to have the same volume. Okay. Temperature in Cardiff. All right. What was the temperature? Temperature was 293 to begin with. Temperature was 293 Kelvin. Okay. Always got to convert to Kelvin when you're doing your Gay-Lussac law. Right, so there's our equation, and we want to know what the temperature in Cardiff would need to be. I'm going to rearrange, so T2, and again, rearrange, okay, and we got a ratio of pressures here. This was 293 to begin with, okay, so 76 was Denver, 100 is the pressure now, okay. And again, I've got a number which is larger than 1 multiplied by this. We are going to have an increased temperature. Now, my temperature is 380, let's say 386 Kelvin. So I have to remember to subtract 273 and convert that into Celsius. Now, does that make sense? We need the temperature of the bottle to be 112 in order to have it expand to the same volume. Okay? Man, I tell you, because the pressure was so low in Denver, there's not many air particles inside that closed bottle. I don't know if you've ever done this on a plane. I've done this before. I remember traveling in South America, and you get an empty bottle, and you're in the Andes, and then you come back, and it's absolutely crushed, and so there's very few particles. So you would have to increase that temperature quite a bit in order to get it to expand and have the same volume as in Denver. Let's see what they say. Right, and I've just caught myself. This needs to be, because the graph was kilopascals, this not 100 pascals. This needs to be 100 kilopascals.
I must have put a decimal point in the wrong place or something. I always do that. I always mess up some mundane detail.
Oh! Well, this is not a mundane detail, Michael!
Okay, so yeah, 100 kilopascals, 100 with a K added in front. Yeah, you could do that as well. Right, and as we see, I should have had a 100 kilopascals or 100,000 pascals. Our answer is 76. Should have been in kilopascals. Okay, so it says allow calculations in kilopascals. We did do that, but we didn't say that was the unit. So, but our graph. We should, okay, well, 1600, well, we had said 1575, so plus or minus 50. I think we're in that. Watch these units. It won't matter when you're doing a ratio because these units should be the same, but just be careful about that. That sort of thing, it didn't matter as well here. Again, I was working in kilopascals. Our answer was correct. We do have, well, yeah, actually, I did get 112.5. Probably I'd round to 113. Okay, so you could also have used the ideal gas law to do this if you wanted to, but I think that's more work for yourself. Okay, and then part B, we've got a question here about explain how the behavior of gases leads to the idea of absolute zero and the absolute temperature scale. Okay, so we can say that distance between the particles or the mean free path, right? It's proportional to the average kinetic energy of the particles, right? Which in other words is saying it's proportional to the temperature. Okay, now we know that distance can get larger when we heat things up, but it also means that if we lower the temperature enough, that the spaces between those particles should get smaller and smaller. That mean free path should get smaller. It should diminish. Usually there's a graph you can have for pressure versus temperature or volume versus temperature, and it will go back and you will extrapolate to this point here, which is negative 273 degrees Celsius. Okay, and we don't like to use negatives, and because we know from our ideal gas equation, because we know PV over T is equal to a constant, we know We can't have negatives in there. We know that's going to mess off the proportionality, and so this is why we've got this absolute temperature scale. Okay, what we do is we redefine the axes, we shift it over. Our temperature is now measured in Kelvin instead of Celsius. We can have it proportional going through the origin, straight line through the origin. Okay, I guess the only other thing we could add is that absolute zero would have to be the theoretical point at which you know, all motion has stopped. Why? Well, because if the pressure is down to zero, it means there's no more collisions with the surfaces of the container. Okay, and I mean, let's face it, at this point the substance is going to be a solid, but a solid is not going to be having particles you know, jump out and hit against the wall. Particles will not be colliding against the wall. No collisions, no forces exerted. No forces exerted, no pressure. Okay, so the pressure would be zero at absolute zero, meaning that all molecular motion has stopped. This is a theoretical thing, although I guess we have gotten fairly close to it in experiments in the last decade or so. Let's take a look at the mark scheme. So what are they asking for? Gas molecules will move slower. They'll have lower energy at lower temperature. The separation will be lower. They will collide less frequently. Yes, okay. Both volume and pressure are proportional to the absolute temperature. We talked about that after. Okay, it doesn't make sense to make that up now because we haven't talked about it. But yeah, absolute temperature is the temperature at which the speed or the energy of the particles we assume would be zero, and therefore the pressure and volume. Okay, and because it's proportional, we'll just keep going lower and lower temperature until they stop moving. Okay, the absolute temperature scale uses the properties whereby zero volume and zero pressure coincide with 0 Kelvin. We do need to say that when we talk about our ideal gas theory, we pretend that the particles are point masses and that they don't have a volume themselves. Okay, I feel like we've got that, but you know, it's really quite condensed. You really do want to practice these questions and make sure you've got 6 points worth. Okay, you can go back and review and see.
George.
Of course. Absolute zero.
Okay, I've got, this might be an Edexcel question. I don't know exactly. I've got this from an old paper of a school I worked at. I just want to take a look at this first question real quick, okay, because this involves kinetic molecular theory. How does sweating help to cool the body down during exercise? Okay, we know it cools down. We know that evaporation is a cooling process. Why is that? Well, which particles are going to be more likely to escape the surface of water that's on your skin there? It's going to be the ones that have more energy. And if those higher energy particles, because if you remember, there's a distribution of energy throughout these particles. It'll be the particles with higher kinetic energy that will escape, and then when they leave, that'll cool the remaining water. That's basically how that works. Okay, I can't draw on here. We'll look at the mark scheme in a moment. What about water melting from ice to liquid in a warm room? Okay, it will stay at 0 degrees Celsius during the melting phase. Yes, it will. Okay, this is why we use ice for these cold drinks. Even though the ice is melting and diluting your drink, what's happening is, because we know all the energy is going towards increasing the internal energy, we know all the energy is going towards increasing the potential energy, not the kinetic energy. The temperature, which is the measure of the average kinetic energy, will remain unchanged. Okay, it's not until those last two ice particles get far enough away to be considered liquid that the temperature will actually start to change. Let's look at the mark scheme and see what they say. So for the first question, any two of the following here. I don't know what year this is from, but I assume this is an Edexcel question. How does sweating keep you cool? Molecules of sweat will have a distribution of kinetic energy. The ones with the highest energy will evaporate. Boom, that could be good. You could talk about how heat from the body will transfer to these other molecules and give them enough to overcome intermolecular forces and evaporate. The loss of the high kinetic energy molecules leaves a lower temperature behind, and that's how it cools you off. Okay, water melting from ice to liquid. Okay, it's kind of similar, right? These H2O molecules are vibrating. Yeah, okay, they're held together by attractive forces. By heat from the room and the surroundings, increasing the kinetic energy of these particles, they will eventually overcome these intermolecular forces and they will melt. Okay, Yes, that's what I've said there. Temperature is a measure of the average kinetic energy. I think if you were to say that in both answers and then give an explanation of that, that would be good enough. I'll let you pause if you need to look at that longer. Okay, and I've got a quick question on Brownian motion here. This is from January 2014, paper 2 at Edexcel. I'm not going to get into observations about solids and liquids and that sort of thing, arrangement of particles. I think that's something that's covered adequately in the base curricula from iRevise. What I want to talk about is the Brownian motion here. An example of Brownian motion, maybe you could talk about little smoke particles floating in the air, molecules or little particles of pollen floating on top of the water. Maybe you've seen this before. How does Brownian motion support the idea that matter is made up of tiny particles in continuous motion? Well, we can kind of see these particles moving around. We can see that the pollen floating on the water, for example, it's moving around. And what's causing it to move around in these random directions? Well, that's because all the other water particles underneath kind of vibrating and hitting it and bumping things. Okay, I'd say something along those lines. Let's take a look at the mark scheme. We got these pollen on the water, dust particles in the air. I'm sure you've seen when the sunbeams come in the room, you can see the dust kind of floating around, just smoke particles in the air if you've got a smoke cell. Accept correct description of Brownian motion applied to unspecified particles in a suitable medium. Okay, well, you could say little particles appear to be moving around in different directions as they get struck by the invisible particles hitting them. Okay. How did Brownian motion support the idea that matter is made of tiny particles? The tiny particles are hitting, colliding, they move around, they hit these larger particles which are then forced to move, and the random motion of the larger particles. Any two of these. You could say that the random motion of larger particles is caused by smaller particles hitting it, and we can see them moving around. Yeah, it's pretty straightforward, isn't it? Okay, and I've got a June 2019 paper 2 here. I've got a little water-filled bag, keeping the doggies cool in the summer. Calculate the energy transferred to dog, okay, by heating in 22 minutes. I don't see... power. There we go. So energy is power times time. So that's 75 watts times 22 minutes. And then, of course, we need to change that into seconds. So we'll multiply that by 60. All right. And the answer there is 99,000 joules. State an assumption you've made when calculating the energy transferred. Well, we are assuming that this is a constant power output, that's not going to vary at all. If we're talking about what's going on here, heat from the dog is going to transfer and warm up the water in the bag, yeah? Now, generally what happens is the greater the temperature gradient, the greater the difference between two temperatures, then the faster the heat will be transferred. Okay, the faster that something will cool down. And you've seen this maybe with your tea cooling or your food, or you're trying to even when you warm something up. But when heat is being transferred, the rate of heat transfer will actually change as the temperature gradient decreases. And when you've got a very, very small temperature gradient of only a few degrees, it takes a long time for it to, equilibrate. But, that might be one thing. We could assume... what other assumptions? I mean, we've already got the one mark. Is there anything else we could say? We could say that we assume there's no other heat flow to the bag. I'd say that's good. Let's move on here. Calculate the temperature of the water after 22 minutes. Okay. Well, our Q equals MC delta T equation is going to be here, and we're going to equate this energy here. The E is now a Q. We'll have 99,000 joules. All right. The mass was 8.7, 4,200 for our rounded up specific heat capacity, and the delta T. Okay, so we're going to have a final temperature minus 16, because 16 was the initial temperature. I'm going to take the 99,000 and divide by this stuff. Okay, and that's a 4,200. Watch your drawings. If you accidentally plug in a 47, that'll throw things off for you big time. I've got about a 2.71 here equals TF minus 16. So I guess I'm going to bring that 16 to the opposite side, and my final temperature, I get an 18.7. Okay, so after 22 minutes, the water has warmed up by 2 degrees. discuss why conduction is the main way that thermal energy is transferred from the dog to the water. Okay. Well, it's not going to be by through the air, because the air is a poor conductor. Okay. It's not going to be convection, because if the hot air is rising up there, and it'll, I don't think you're going to get a convection pattern from the small, what's the temperature difference between the air and the dog? It's only maybe, what, 10, 20 degrees? I think what we're looking for here is the dog and this plastic or water, rubber-filled bag of water, they're in contact with each other. And yes, there's water as a liquid inside, but this bag is solid. They're in quite a bit of thermal contact. Because there's a difference in temperatures, we know that heat transfers from a hot body to a cool body. Okay, and so because they're in contact and there's a temperature gradient, the heat will flow. It will be done through conduction. I would say something along those lines. Shall we take a look? Right. So we substitute in, and we get our equation subbed in, and we get 99,000 joules. One assumption that was made, the dog does not change temperature. Okay, yeah, I guess the dog would be cooling down. The dog does not change power output. Maybe all of a sudden it's giving out more heat or less heat. Okay, the rate of transfer is constant. Yep, no heating from outside. Oh, watch this. No heating from outside, no heating of outside. So there's no other exchange of heat. That's the assumption we had made, okay? I think I'd said that the power rating was constant, which I mean the power output of the dog, okay? Anyways, that was 1 mark. We plug everything all in here, and I had 18.7, so we'll round that up to 19 degrees. Accept answer to 3 or more sig figs. Okay, make sure with your exam boards you know how many sig figs they'd like you to have, how many decimal places, that sort of thing. Okay, but we've got the 4 marks there. Equation, substitution, we multiplied out, we got the temperature change. Okay, and why is conduction the main way that this dog's going to cool off? The dog and water are at different temperatures, and they are in contact, so they're in thermal contact, so there will be a transfer of heat. No movement of particles from dog to water, so not convection. Okay, yeah. Dog and bag are both solid, so convection is impossible. Not much radiation, as they are at similar temperatures. I had said that as well. Okay, so there's a few things you need to know. This is a bit of a review of conduction, convection, and radiation, and yet at the same time it's just a little bit more advanced than other questions you see regarding this sort of thing. And here I have a June 2015 paper 1 from Edexcel. In this question, it's talking about these hard drives. They're both connected, so they receive the same amount of electrical power. We would imagine that they do the same amount of work, and so the temperature rises the same, and they're going to compare the 2 different configurations. Hard drives are working, but their temperature is lower than before when you have the black one on top. Okay? Explain why the hard drives work at a lower temperature when the black one is on top. Okay? Well, you could say a few things. Right, now you might instinctively look at the white one and think, hey, it's going to be reflecting all that light. It's reflecting the infrared away from it, and we know that the black object will be absorbing it. Because black is a poor reflector, it is a good absorber. If something is a good absorber, it is also a good emitter. So even if these were at the same temperature, the black one is going to radiate more infrared radiation away than the white drive will. So this is what you want to explain. You could just say, hey, surface areas are the same. If you've got one on, if the black one's on the bottom, all you've got is this little edge around. Okay, if it's on top, you've got that plus this whole surface here. So the 2 together, if you are going to stack them, I wouldn't recommend stacking hard drives, but that's, that's neither here nor there. The point is, this is going to radiate much more heat, and the 2 will be cooler in general. Okay, we could be talking about, some of the heat from the white might transfer to the black and be emitted that way. let's take a look at the answer. There's 6 points here that you could say here to get the 4 marks. Okay, so infrared radiation is something that I had mentioned. Okay, the emission of thermal energy, and then the correct effect for the correct surface. So I'd said black was a good emitter, white was a poor emitter. You would just need to say one of those. Okay, we can compare the surfaces. If you like, the black loses more heat than the white. That's what they mean. Okay, correct statement about thermal energy flow at equilibrium temperature. So once they get down to a certain temperature, which way is the energy flowing? What would you say? Okay, I didn't really talk about that. Back up to the one here. I wanted to save this for the end. Don't talk about conduction, convection, absorption, or reflection. You don't say about anything of those. This is about black body radiation, and that's basically it. Okay, you could talk about the transfer of heat by conduction because the two are in contact. They are in thermal contact with each other. Okay, you know, we could say that they've got the same surface area. Okay, if you wanted to talk about some transfer between them. Okay, but the main thing for the 4 marks is what we've already talked about here. Okay, anything in these first 5 will get you the marks you need. Your job is, of course, to practice and articulate the physics of what you know, and that you are earning the points allotted for each question. Okay, and the last of our thermal physics questions, I've got a paper 1 here from AQA, June 2017. This is a 6 marks word question. I don't want to dwell too much on it. I think there's some black body stuff here, but you know, this could serve as a nice review of conduction, convection, and radiation as well, even though we had said that was covered elsewhere. Why is design A better than design B? Okay, I can't write on these pages, so let's just have a quick cursory look. Right away I see insulation on design A, so of course it's going to heat things up faster. It has insulation. Okay, what else can we say here? All right, we can take a look at the pipe that the water's flowing through is black and metal. We can say black is going to be a better absorber of heat, so some of that heat's going to go right to the water. Okay, it's metal, which is a far better conductor than plastic. Okay, the fact that you've got white plastic versus black and metal, they're actually polar opposites of what you would want. Okay, the design B is the opposite of everything you would want. All right, inside they have a dark matte surface, and that's just going to absorb more heat. We don't want that. We want an inside surface to be white and shiny. It will reflect any heat back into the solar panel. It will therefore hit this black metal pipe. It's like when you barbecue, you wrap the food with the shiny side facing in to reflect all the heat back in on the food. Okay, and I guess one other thing you can look at is, if you'll note, there is a longer length of pipe in the solar panel A, whereas with design B you can see the area or the length of the pipe inside is not as much because it doesn't have as many turns. Okay, so this is you know, it's just a matter of the surface area, and there's more surface within there, more pipe to gain the heat. Okay, and the mark scheme here, your answer, part of it will be determined on the quality of your written communication, clear, correct explanation, and how most features of design A are better than B. So there's plenty of things you could have talked about. As you can see, color of the pipe, going to absorb more IR. It's metal, it's a better conductor, better than plastic. Higher rate of energy transfer through the metal. The color of the surface, the white shiny, is going to reflect heat to the pipe. And also the fact that this white shiny surface is a poor absorber of IR radiation, which means you're going to have more heat available to go to the pipe. Whereas here, if it's dark matte, you're going to have a lot of that heat being absorbed by that material, and it won't reflect back to the pipe. So I guess there's 2 ways you could say that. Okay, we talked about the insulation, the length of the pipe. Okay, and because it's metal, it'll be faster. Okay, so design has greater water temperature increased. And you could talk about any of those things. So I hope you've done that. Like I said before, you really want to craft your answers. You really want to break it down. I'm just going through the physics here of what you should know, just reminding you, okay, how you might think this out. It's going to be your job to craft your solutions and be a wordsmith and kind of make sure you are using scientific vocabulary, you are being efficient and concise, and that you've got a good flow to the answer.
Well, it certainly looks like a lot of words in record time. I'm very impressed with both of you.
Thank you.
Unfortunately, I am also disgusted This is incoherent drivel. This is a total redo. And I'm assuming I need it right away.
Yes, this is the last of our GCSE supplementary series from iRevise. I hope you've enjoyed them, and I hope we've covered everything that is particular to your exam board. Of course, try to get in as to many past papers as possible and get as much practice as you can. Thanks for watching, and take care.